let's say I want to know the average velocity of an object. Well, I would take the position, and I'll use P for position, the position at one value, like at B, minus the position at the beginning, divided by the change in time. So it's the change in position over the change in time. But if we wanted instantaneous velocity, what would I do different? So instantaneous velocity, velocity at a single point in time, exactly what your odometer tells you or your speedometer tells you when you're driving. That would mean that we'd want these 2 points to actually be in the same spot. So I'd have to find the limit as A approaches B or as B approaches A. So another way we can do that is find the limit, and I'm going to write it a little different, as H approaches 0 of my position at A plus H minus my position at A divided by H. What does that look like? It looks like the derivative. And it is. Let's say I have a position function that says that the position of an object is 4.9 times squared. And then I want to know, so here's the position of an object. Let's see, what is the velocity after 5 seconds? Well, let's think about velocity here. Velocity would be the change in position, right? Okay. The limit as H approaches 0 of, and I'm going to plug in A plus H first. And the first time I'm going through this, I'm just going to do A plus H. You'll see why in a second. Minus we're going to come up with a formula, and I wish I hadn't used A because that might be confused for acceleration, but we'll deal with it. What am I going to get when I take this and square it? Well, I'll come off to the side. That's going to be A squared, AH, and another AH. That's 2AH plus H squared. Okay. I'm going to distribute. Notice that the first term and the last term go away. And these two both have an h. So I could factor out the h, or I could just divide each term by h. And I will get 9.8a plus 4.9h. Now, when I let h go to 0, this term is going to go away, and I'm going to be left with 9.8 times a. In other words, I can find the velocity anywhere on the path of this object by taking 9.8 times 5. This is the velocity at time 5. Now, could I have plugged in 5 for my a's? Yes. And it would have also given me the same answer. I believe that is 49, and it would be meters per second. So we can use these derivatives, this difference quotient, to find instantaneous velocity or instantaneous rate of change. So average rate of change it's the rate of change over a time period, kind of like average velocity is over a time period. Instantaneous velocity is, or instantaneous rate of change is at a single point. It's going to be the derivative.